the absolute value of the inner product of AW with W is equal to the supremum of the inner product of AX with X taken over the unit ball. So that's essentially like an extreme value theorem, sort of, if you look at that one, right? I mean, it's kind of like an extreme value theorem. You see what I'm saying? So the supremum, are we good? I think you can see it now, right?
Yeah.
Yeah. So A compact means that the values of this, right? Well, there exists a W such that the value of this thing is equal to the supremum of all such terms taken over the unit ball. This is the extreme value theorem, but this time for a compact self-adjoint operator on a Hilbert space. So, I mean, because essentially you're attaining the maximum, if you will, here, like that. All right, so what remains here in this section is that, the theorem right before this was that if A is a compact self-adjoint operator on a Hilbert space, then at least one of the numbers norm of A or minus the norm of A is an eigenvalue of A. All right. The theorem after this is that the eigenspaces corresponding to non-zero eigenvalues of a compact self-adjoint operator are finite dimensional. So that's kind of neat. All right. So you get a finite dimensionality of the eigenspaces for a compact self-adjoint operator. Theorem 4.9.19 says that the set of distinct non-zero eigenvalues of a compact self-adjoint operator is either finite or countable, and if you put a sequence of them, they have to limit to 0. He gives an example of an operator on L2 to illustrate this. Then theorem 4.9.21, he has a sequence of pairwise orthogonal projection operators on a Hilbert space H, sequence of numbers that limits to 0, and so he looks at an infinite series formed by an infinite series of these orthogonal projection operators. He argues that they're bounded. They give us a bounded operator on the Hilbert space. He builds the operator A as an infinite series of projection operators. All right, in part B. He has the theorem that if all of the eigenvalues are real, then A is self-adjoint. And if all of the projections are finite dimensional, then A is compact. So this is very cool. And then the last part of the section, he introduces something called an approximate eigenvalue, and he has like a theorem about approximate eigenvalues and how they interact with compact operators. The theorem about projections, I think, is most interesting. So just to tell you guys a minute here, if you have, let's say, AU1 equals to lambda 1 U1, AU2 equals to lambda 2 U2, AU3 equals to lambda 3 U3, and let's say U1, U2, U3 orthonormal. So they're orthonormal eigenvectors, all right? You can build the formula for A using these matrices like this. You can write A is equal to lambda 1 U1 U1 plus lambda 2 U2 U2 plus lambda 3 U3 U3. Now, to make those make sense, I need some transposes, right? I'm talking about 3 dimensions, so these are 3 vectors, right? So you guys tell me, does the transpose go on the first vector or the second vector? What has to be the case in terms of, we got what, 3 by 1 vectors? We're trying to make a 3 by 3 matrix. So I think I need the transpose on the second vector, right? Think about that. So, because then I have a 3 by 1 times a 1 by 3. And so my argument is that that has to be A. That has to be A. And so what are these? How does U1 U transpose work? Like it's, well, you got the outer product, but how does it work? What is this mapping? What is this matrix? Check it out. If you let U1, you get back U1. On the other hand, if you put in U2 or if you put in U3 into this, what happens? You get, because they're orthogonal, right? Those are dot products of U2 and U1 or U3 and U1, so those are 0. So what you're looking at, this and that which I'm about to underline in red, these are projection matrices. They project onto respectively the first eigenspace, second eigenspace, and third eigenspaces of A. And so you see what we've done is we've written A as a sum, j equals 1 to 3 of lambda j pj, where pj is a projection operator. Well, it's a projection matrix, all right, on, again, to the jth eigenspace. So the theorem that I haven't written on the board that I just talked through is the infinite extension of this idea, where you have a sequence of eigenvalues and you're building a series of projection operators like this. But these are kind of fun. Like if you want to create a matrix that has eigenvectors that you like, you can work backwards and put the eigenvalues you want. You know, if you have an orthonormal basis, you can reverse engineer and make matrices with whatever eigenvalues you want using this trick. This is how I sometimes make up examples. That's not the easiest way to make examples. The easiest way to make examples is start with a diagonal matrix and conjugate by a unimodular matrix and be a reasonable person to use a computer algebra system. But anyway, I think that's it for today, Audric. So I will stop here.
Yeah.